Every motion you see, whether it's a basketball flying toward a hoop or a car driving down a straight highway, can be mapped perfectly onto the x and y axes of physics. To understand how objects move, we start in one dimension. Acceleration is strictly the rate of change of velocity over time. If a car speeds up, that change is mathematically written as a equals dv over dt. By taking the integral of that core definition, we arrive at our first baseline equation. It tells us that final velocity equals initial velocity plus acceleration multiplied by time. Following that exact same mathematical logic gives us the rest of the set. Integrating again yields the formula for displacement, and combining them provides a third equation to find final velocity squared when time isn't known. There is a catch. These three formulas only work under one strict condition. The acceleration must be perfectly constant. If it changes, these equations break down entirely. Moving into a two-dimensional plane relies on one rule. Horizontal and vertical motions are completely independent. What happens on the x-axis stays on the x-axis, and what happens on the y-axis stays on the y-axis. When you combine a constant horizontal velocity with a changing vertical velocity, driven downward by gravity, the object traces a parabolic arc. This creates projectile motion. To find the total time of flight, we look solely at the vertical axis. When the projectile lands back on the ground, its net vertical displacement is exactly 0. Setting y to 0 allows us to easily solve for time. We build the other formulas the same way. By isolating the highest point on the y-axis, we calculate maximum height. By mapping the total distance covered along the x-axis during that flight time, we get the range. You never need to blindly memorize a massive list of projectile formulas. If you know how to isolate the x and y components, you can construct them on the spot. The most common calculation error in exam conditions has nothing to do with complex algebra. It is failing to lock in a strict sign convention. If you define upward initial velocity as positive, then downward gravity must be written as a negative value. Examiners also exploit the maximum height trap. Many students assume an object stops completely at the top of its arc. The vertical velocity is 0, yes, but the horizontal velocity is still pushing it forward. Let's test this right now. Pause the video and calculate the maximum height for a projectile launched at 20 meters per second at a 30-degree angle. Use 10 for gravity. Here is the correct substitution. You take the initial velocity squared, multiply it by the sine squared of 30 degrees, and divide by 2 times gravity. The entire expression reduces cleanly down to exactly 5 meters. Catching minor unit conversions and holding your sign conventions steady during these calculations is exactly what separates an average score from a top medical rank. This chart shows velocity over time. To calculate total displacement from this graph, you isolate the shaded area under the curve. Do not calculate the slope. Exam writers know that rushed students will instinctively calculate that slope. They intentionally include that incorrect mathematical value as one of the multiple choice options just to catch you off guard. In two-dimensional motion, remember the complementary angle rule. Launching a projectile at an angle of theta, or 90 minus theta, will result in it hitting the exact same horizontal target on the ground. Here is a complete summary card covering core 1D equations, 2D projectile derivatives, and strict sign rules. Save this for your final review. Mastering kinematics comes down to trusting logical derivations and setting up your axes correctly. Once the initial setup is precise, the math simply solves itself.
Thank you so much for watching. Subscribe our channel and stay updated for more lectures.